So let's do a little bit of review before we dive into new things here. So, oops. Hello. So let's take a look at this example. Is this a polynomial? What do you guys think? So yes, okay. Chloe, you said yes. Why did you say yes?
Because the exponents go, or like the highest point first and then it goes.
Okay, so that just is talking about standard form for a polynomial. That's not exactly why something's a polynomial. But looking at the exponents is what you want to do. What do you want to see in the exponents? A number, okay. Specifically, what kind of a number? A positive number. And what else? Whole. Got to be positive whole numbers in the exponent, which is what we're seeing here, right? Everybody agree with that? So what would something that's not a polynomial look like? Is this a polynomial? No. Okay, why not? Okay, so we have a negative in exponent. That's good. Is there any other reasons why it's not a polynomial? Okay, we have a 1/2 in the exponent. Anything else? The square root 7, is that okay? It is. Why is the square root okay here? It's not because there isn't an exponent, because it's only around the number part, not around the variable part. So the square root of 7, thank you, Connor. The square root part is only around the 7. The square root of 7 is just a number, right? It's a decimal, but it's just a number. Everybody agree with that? So that's just a number times a variable. That's fine. What wouldn't be fine is if we had that. That's not okay in a polynomial. Why not? Yeah, because the square root is now over the x also. Everybody good with that? The difference there? So just got to be a little bit careful about that. So for this example, we're going to put the polynomial in standard form and then list the degree, the leading term, the leading coefficient, the constant term, and the number of terms. So let's do the standard form part first. When we write this polynomial in standard form, what's the first thing that we need to write? -10 x to the fifth. Good. Why's that one got to go first, Chloe? Because it's got the biggest exponent. Very good. What's going to come next? Good. 6x cubed. And then after that, 7x squared. And then negative 7x. Yep. And then plus 8. Everybody good with how to write it in standard form? That should be pretty easy, right? What's the degree for this polynomial? 5. Why is it 5? It's the biggest exponent. Good. What's the leading term? X to the fifth. Negative 10x to the fifth is the leading term. What's the leading coefficient? That's negative 10. Okay. The constant term, what's that? 8 is correct. And the number of terms here is? It's 5, right? We have 1, 2, 3, 4, 5 terms. Everybody good with that? Okay. So next we'll simplify each polynomial expression. So I'm going to define an f of x and a g of x So for the first one, we're going to figure out what f plus g of x is. Oops, that was supposed to be key there. So if I want to do f plus g of x, what do we really need to do here? What was that, Chloe? F of x plus g of x, great, which basically just boils down to doing what? Combining like terms, right? Okay, so when we combine the like terms, let's write our answer in standard form. So what's the first part of our answer we should write? X to the fourth, good, and then good, 7x to the third, or 7x cubed, good, and then what? Close. So these combine, right? So we get negative x squared. Negative 2 plus 1 is negative 1. Okay, and then what? Good, 4x, because we combine those two together. And lastly, we get 1, combining those two together. Everybody happy with that? Addition should be pretty easy, right? Not much to it. What if we do f minus g of x? If we're subtracting, does anything change? So we do have to be a little bit careful here. So my value for f of x, nothing really changes. But remember, I'm subtracting all of g of x. So what do we have to worry about when we put a negative sign out front of a parenthesis like this? Yeah, that negative has to distribute to everything. So I now have a negative 7x cubed, a negative x squared, a positive 3x, and a negative 4. So when I combine like terms now and write my answer in standard form, what would I get? Good. Good. Very good. Very good. Very good. Everybody happy with that? So, again, not too bad there, right? The only thing we have to really worry about is making sure we distribute that negative across the entire polynomial. And then everything else is just combining like terms. What if we do f times g of x? How do I do that? Elena? Yeah, let's make the grid. Yep. So I'm going to put f of x as my as the top of my grid. So I'm going to have x to the fourth, and then what's going to come next? I'm going to have 0x cubed. Why am I putting that there? So everything lines up. Yeah, so notice we go from x to the fourth to x squared, and we have no x cubes. So for this grid to work in its best way, we need to put a 0x cubed there to kind of fill that spot. Then I have minus 2x squared plus 7x, and then minus 3. And then going down the other side, I have 7x cubed plus x squared minus 3x, and then plus 4. Everybody okay with how I set my grid up? Okay, now we just have some multiplying to do. So the first box should be 7x to the 7th. And then we have 0x to the 6th, negative 14x to the 5th, 49x to the 4th, and then negative 21x to the 3rd. Notice if I look at the exponent as I move from left to right, what do you see going on with the exponent? Goes down by 1 each box. Very good. And now I'm just going to continue filling in each row. Oops. Notice also if I look up and down my grid, what do you notice about the exponents? Okay, they do line up diagonally, but we're also decreasing 1 as I move from top to bottom in each row or each column, right? So the rows decrease as you go from left to right, and the columns decrease as you go from top to bottom. So to combine our like terms, we're going to look along the diagonals because all my like terms are on a diagonal with one another. So if I do that, I have 7x to the 7th, and then x to the 6th plus 0x to the 6th is just x to the 6th. Negative 3x to the 5th plus 0 plus negative 14 is negative 17x to the 5th. Then if we look at x to the 4th, so we have 4 plus 0 minus 2 plus 49, so that's 51 for x to the 4th. And then the x thirds, I have 0, 6, 7, and then negative 21, which is negative 8. Then if I look along the x squareds, I have negative 8, negative 21, and negative 3. What's that? Negative 32. And then if I look at the x's, I have 28 and 9, which is 37. And then the constants are just negative 12. So there's my answer. Everybody okay with that? So again, like that problem would be real messy to try to FOIL out by hand doing like an extended FOIL. There's a lot of stuff to kind of keep track of. The grid makes it really easy to not lose track of any terms. Makes it really easy to find the like terms to add together, because if I multiplied this out by just like an extended FOIL, I would have ended up with 16 terms, and then figuring out which ones are like terms, like having to search through to make sure I've counted all of them or didn't double count anything, or, you know, this is so much easier from a logistics standpoint. So that's what we had done last week. Today we're going to start talking about 2 new topics. Those topics are synthetic substitution and then polynomial division. Before we start talking about synthetic substitution, I just want to talk about like substitution with functions first. So let's say we have this polynomial. And I ask you guys to evaluate or find the value for f of negative 1. Oh, thank you. What does that mean? What are you supposed to do when I write evaluate and then write the symbols f of negative 1 like that? Chloe? It's not going to be multiplying the equation by negative 1. So, Chloe, what that would look like, it would be negative 1 times f of x. That's what multiplying the equation by negative 1 would look like. So this looks different, right? That's what we do want to do, yes. So what this says is plug negative 1 into the x's and then find what that equals. Everybody okay with that? So in practice, what we would say then, f of negative 1 is equal to negative 2 times negative 1 cubed plus 3 times negative 1 squared plus 5 times negative 1 and then minus 6. So negative 1 to the third, well, that's negative 1 times negative 1 times negative 1. Negative 1 times negative 1 is 1, and when I multiply by negative 1 a third time, I just get negative 1 again. Negative 1 squared is negative 1 times negative 1, which is just 1. 5 times negative 1 is negative 5. And then negative 2 times negative 1 is 2. 3 times 1 is 3. And when I combine all those like terms, what I get is 6. So our answer, we would say f of negative 1 is equal to negative 6. So this is something you would have done in an Algebra 1 course. When you talked about functions and function notation, you would have done done exercises like this. What I'm going to present today is another version of a way you can do this only for polynomials, called synthetic substitution. So let's say we still have that same f of x. And we're still interested in what f of negative 1 is. Okay? So this is an alternative way to do the same thing we just did above. What we're going to do is we're going to start by drawing this bar. So this is just part of the setup for the problem. I'm going to take whatever we're plugging into f and put that outside of the bar. And then I'm going to take the coefficients from f and put them inside the bar. Everybody okay so far with the setup? Okay. So the first step is I'm just going to take that first number inside the bar and just write it down below the bar. It's always the first number, always the first step. That's the first thing we do after we set up the problem. Now what I'm going to do is I'm going to multiply the number on the outside to that number below and write it above the bar. So negative 1 times negative 2 is positive 2. And then I'm going to add down. And that gives me 5. Yes?
And then you multiply the outside by the one that we brought down. And then
We write that answer above the bar.
and how we get 5.
We add it down. 3 plus 2 is 5.
So like negative 1, you got from like f times 1.
That's not f times 1, that's f of 1. Yep. So f times 1 is something different. F of 1 is what we're looking at there.
Could you put like any number in there?
Well, we didn't put the negative 1 there. That was the problem. We're looking for what f of negative 1 is. But there's nothing magic about negative 1. It's just a number. So, like, it could have been anything, but for this example, to practice this synthetic substitution, I chose it to be negative 1. Right? This was part of the problem. Yes. Yeah. We didn't pick that for any reason. So the next step now, I'm going to take my negative 1. I'm going to multiply it by the 5. Write the answer above the bar. And then add down. Everybody so far so good? And I'm just going to kind of keep redoing that same process until I run out of spaces. So I need to do it one more time. So negative 1 times 0 is 0. And when I add down, I get negative 6. And this is the part that I need. That is going to be my answer to f of negative 1. Notice that this was the same problem we did above using our Algebra 1 knowledge. And we're getting the same answer here that we did before, right? Everybody notice that? Still getting the same thing. So you might ask, why do we need a second method to do the same kind of problem we already know how to do? Fair enough. This new method, not any really particularly faster or easier to do. And you're right, not a great substitution method. The advantage here is we can use this synthetic substitution to do things other than substitutions. We'll look at some of those applications later on in this, in this unit. And it turns out that these other numbers that are left over down here that we ignored have some meaning if we look at this in a slightly different context. And I can take this synthetic substitution technique and tweak it just a little bit, and it becomes really time-saving and useful to do something else. So I just want to introduce this concept now so that when I want to pull it off the shelf to use it in another section or two, it's there and we have it, we're capable of using it. Because in the next chapter, we're going to do so much with this that you really need to be good at it. Okay? And we'll talk about how we'll use it in the next chapter, but it's super useful and super time-saving to be good at this. Everybody okay with that idea so far? Let's do another example, okay? So let's say this time our f of x is and say we want to do f of 2 this time. So that's what we're interested in. All right. Well, I'll start by setting up my problem. So I'll draw my bar. What number is going to go outside of the bar? A 2. Everybody's good with that? What numbers are going to go inside the bar? 3, -2, and 7. Now you'd think that, right? It's not quite that. You're missing some things. So if I look at f of x, I go from x to the 4th to x squared. What am I missing? We're going to need a 0 for the x cubes. Also then notice that I go from x squared to just a constant. So what's missing there? The x's. Elena. Yes, to account for the things that you're skipping. You'd have to put 1 0 in between the for the x to the 4ths that you're missing, and then 3 zeros at the end for the missing x squareds, x to the first and constant. If you add x to the fifth plus something to the x to the third. So you need 1 in between the two and then 3 at the end. Yeah, 3 at the end. Everybody okay with that? Do those zeros have to be here? Yes. This will be wrong if you forget to put in the zeros. The zeros must be there or things are not going to work out. Unlike the grid where it's just inconvenient to forget the zeros, here, if you forget the zeros, it will not be correct. All right. First step, we are going to bring down that first number. And then we multiply the number on the outside by the number below and write it in the next spot above. And then we add down. That gives us 6. Everybody happy with that? Okay. Next step. Going to take the number on the outside, multiply it by the number below, and write our answer above, and then add down. Yes. Sure. See you later. And we'll just keep going, right? We have 2 more spots to fill, so we'll just keep on going. So 2 times 10 is 20. And then we'll add down. And then we'll last step, 2 times 20 is 40. And then we add down to get 47. So our answer would be 47. So note, when I drew these arrows in, see all these arrows all over the place that I drew in? Do I expect to see those on your paper? No, you do not need to include those. I just included those so that when you're looking at the notes, it makes sense kind of what I'm doing and where things are coming from. Again, when it's the first time you're seeing this, I'm going to try to be, like overload you on notation there a little bit to make sure if you go back and look at things, you can tell what we did there, because if you look at the notes without watching the video, if we just had the numbers there, it wouldn't make a ton of sense, like where things came from, right? Hopefully the arrows add a little bit of narrative for us. Everybody okay there? Okay. Do we feel okay doing this synthetic substitution? Should be relatively easy, right? All we're doing is multiplying and adding. The procedure is the only thing that's a little bit tricky, but once you've done it a couple of times, you should be good. The hardest thing to remember is to include the zeros. Yeah, can't forget to do that. All right. The next topic that we need to talk about is polynomial long division. Before we do that, though, let's review just how to do regular long division. Now, this was a question that I used to not have to ask, but it seems like more and more this is something that kind of gets fast-tracked through in elementary schools. How many of us remember how to do long division by hand? Okay. All right. I mean, it happens. All right, so let's do one here just to review, because the same principles we're using to do numeric long division are going to apply when we do polynomial long division. But this is a little bit simpler if we start with just a regular long division problem that most of us are pretty comfortable with. And you'll see the similarities right away, okay? So let's say we want to do 7,596 divided by 26. So just as a little bit of vocab, this number is called the dividend, and this number is called the divisor. When we set up our division problem, we write a division bar, and then which number goes outside of the division bar? The divisor. Good. And what number goes under then? The dividend. Everybody's happy there? Okay. So what we do then is we ask ourselves a series of questions. We first go, okay, how many times can 26 go into 7? Well, 0. Okay, well, how many times can 26 go into 75 then? Well, it can't be 3 times, because 3 times 25 is 75, right? And 26 is definitely more, so it's only going to be 2 times. So we do then 2 times 26, write it below the 75, and subtract down, right? That gives us 23, and then we bring down the next digit. Everybody's okay there? Okay. Then we ask ourselves the same question. We ask how many times, stop talking please, does 26 go into 239? Well, it's got to be less than 10 because 10 times 26 is 260, right? It's got to be less than 9 because 9 times 26 is... No, it's 9, so it's 234. Bring our next one down. And then how many times does 26 go into 56? Or twice. 2 times 26 is 52. We subtract down and we get 4. What do we do then? We write remainder 4. Everybody remember kind of doing this? So we'd say our answer then to this problem is 292. We call this number the quotient, just FYI, plus the remainder over the divisor. That's true if you're looking for the decimal. If you just want it written as a mixed number, like we've done here, we would stop with the remainder. And I think that's usually the first time you see long division is you still have remainders, right? So this process is when you still were working only over the rational numbers, where you didn't have the real numbers and couldn't just like write a decimal as long as you needed. Massimo? Sure. Okay. So we kind of remember this process, right? It's not too bad. The hardest part is usually trying to figure out which number goes up here, because sometimes it's not obvious, like how many times, like 26 went into 239 or something. Like that was a little bit tough to come up with, right? You guys remember that? We just saw it a second ago. The nice thing about polynomial division is that it's actually easier to figure out what the numbers on the top are. It's actually pretty easy to do that. So let's do an example. Or a couple of examples, excuse me. Okay, so let's say we have x cubed plus 6x squared plus 11x plus 7 divided by x plus 3. on sheer money. Okay. So we'll start by drawing our division bar. What number, or what, I guess I should say, what polynomial is going to go outside the division bar? X plus 3. And what polynomial is going to go under it? The dividend, right? Everybody so far so good? Okay. Here's the nice part about polynomial division. All we care about are the leading terms. So I'm just going to ask, what times x gives me x cubed? X squared. Everybody agree with that? Okay. So I'll write an x squared here, and I'm going to multiply it to both parts of the divisor. It's going to give me x cubed plus 3x squared. Here's the place where most students are going to make their mistakes. Now we subtract down. Notice that I wrote that parenthesis around the entire thing. When I have a subtraction symbol in front of a parenthesis, what do I have to remember to do? Yeah, I need to distribute that negative, right? So this x cubed becomes negative, and that positive 3x squared will also become negative. Everybody okay there? So x cubed minus x cubed is 0. So we're good there. 6x squared minus 3x squared is 3x squared. And then I'll bring the next term down. And I'm going to now repeat the process. I'm going to say, what times x gives me 3x squared? Or 3x? Right? 3 times 1 is 3. X times x is x squared. Everybody's okay with that? So that's going to multiply by both terms of the divisor. So I'm going to get 3x squared plus 9x, and then we'll subtract down. Everybody good there? What do I need to make sure I do here? I have to distribute my negative. So that's going to turn into a negative 3x squared and a negative 9x. 3x squared minus 3x squared is 0. 11x minus 9x is 2x. And then I'll bring the next term down. And then I'm going to ask, what times x gives me 2x? 2. So I'll write plus 2, and then I'll take that and multiply it by each term and subtract down. What do I need to remember at this step? Distribute that negative. So I'll end up with a minus 2x and a minus 6. When I subtract down, I get 1. Can x go into 1? No, right? There's just 1. So that's my remainder. So the way that I would write my final answer then, this is equal to x squared plus 3x plus 2 plus the remainder over the divisor. Let's do another. Sound good? Okay. Actually, let's do okay. So, let's set this up. So I'll draw my division bar. What polynomial is going to go on the outside of this division bar? X squared plus 1. How am I going to write it? I'm not going to write x squared plus 1. X squared plus 0x plus 1. Why am I putting the 0x there? Because I'm missing the x's between x squared and then the constant term, right? What am I going to write underneath the division bar? That's not what I'm going to write. Because what am I missing? I'm missing the x's. So I need to make sure I put the 0x there. So again, we got to be, you're going to see in a moment. Right, x to the firsts. Right, just the regular old x's. That's what we're missing in each of those. Exactly right. So we're going to include those zeros there because they're going to make sure that everything lines up with like terms when we do the subtracting down. So it's not mandatory that the 0x's are there, but in my experience as a high school math teacher, I have never seen a student do these problems correctly that didn't include the zeros. So if you are skipping out and doing the zeros, you're probably going to end up making a mistake and doing the problem wrong. In my 10 plus years of doing this, I've never seen a student leave the zeros out and consistently do the problems correctly. So they're maybe once in a long while, if the problem is very simple, they end up getting the right answer anyways. But if there's more than one step to it, almost always they screw something up along the way. So you really need to put the zeros in. It's really to your advantage. All right. So we'll start. What times x squared gives us x to the fifth? X to the third. So I'll multiply that then to all the parts of my divisor. That gives me x to the fifth plus 0x to the fourth plus x to the third. And then we subtract down. You see now why I wanted the 0x there, right? Because where would that x cubed I would end up writing under the x to the fourth? And then if those don't make sense to combine together, so you have to be paying enough attention not to combine those together and combine it with the x to the thirds that are not lining up right where it's supposed to. It just makes life much, much neater. You have to be much less careful on a problem that you already have to be pretty careful about if you put the zeros in. All right, let's distribute the negative through. So x to the fifth minus x to the fifth is 0. Negative 4x to the fourth minus 0 is still negative x to the fourth. 2x cubed minus x cubed is just x cubed. and then we'll bring down the next term and repeat. Ask ourselves, what times x squared gives us negative 4x to the fourth? It would be negative 4x to the second. Good. Then I'll distribute that to each of the pieces. Give me negative x, or negative 4x to the fourth, minus 0x to the third, minus 4x squared. And then I have to subtract all of that down. I'm going to go and distribute through the negative, so that negative 4x squared is going to become positive. The 0 is going to be positive. That doesn't really matter because it's 0. And then the negative 4x squared is going to become positive. So, negative 4x to the fourth plus 4x to the fourth is 0. X to the third plus 0 is x to the third. 2x squared plus 4x squared is 6x squared. We need to bring down the next term. And we'll ask ourselves, what times x squared is x cubed? X, right? Everybody agree with that? X to the first would be fine as well if you want to write it that way. So multiply that. Each piece of the divisor, and then subtract down. To do that subtraction, let's distribute the negative. So each of those becomes negative. And when I add down, I get 6x squared minus x, and then plus 7. Everybody good? All right. One more step. How do I know there's one more step? I'll tell you in a minute. So what times x squared can give me 6x squared? 6. I'll multiply that. Each part of the divisor gives me 6x squared plus 0x plus 6. And we subtract down. So when I distribute the negative, each of those become negative. And I'm left with negative x plus 1. Now, if I ask myself how many times can, or what times x squared gives me negative x, nothing, right? There's not a polynomial that I can multiply by x squared to get x, right? So that's all going to be my remainder. Furthermore, I knew that was going to be the remainder because I had just done my constant term, right? So I know that there can't be anything after the constant term in a polynomial. That has to be the very last thing. So, the way I'd write my final answer then is x cubed minus 4x squared plus x plus 6. Remember, what do we call that part as a name? It's the quotient. And then we have plus the remainder over the divisor. What do you guys think? Takes some time, but it's not so bad, right? it's actually a little bit easier to figure out what the pieces of your quotient are going to be than it is with regular long division, because it's really easy to figure out what do you have, like what times a monomial gives you another monomial, right? That's really easy. So it's a little bit easier in a way to kind of like peel that out. The place where you have to be really careful, well, it's twofold. You have to make sure you get the zeros in if you need zeros. And then the other place is making sure that you're distributing that negative appropriately, right? Those are the two places where students tend to make mistakes when doing this. If they know what they're doing, those are the two places they typically will make a mistake, if they generally have the idea down. Now, there's certainly students that have no clue what they're doing and just like make an ungodly mess of the whole thing. Like that happens. But that's just because you had pieced out for like 2 weeks and didn't bother to do any homework or whatever. That's a different story. But if you've been trying and paying attention, the places where typically mistakes get made is forgetting the zeros or forgetting to distribute the negative. So those are the two places you got to be careful about. Okay, well, we'll stop here.